Good day everyone. I am Carlinhos Sarocam together with my partners Justin Ray Ulinaw and Carlo Rubi. So today we are going to share our ideas about hyperbolic geometry. So hyperbolic geometry, a world beyond Euclid. Hyperbolic geometry is a non-Euclidean geometry, meaning it deviates from the traditional axioms and postulates of Euclidean geometry. So imagine a world where parallel lines can curve away from each other. Triangles have angles that add up to less than 180 degrees, and circles have infinitely many centers. This is the realm of hyperbolic geometry. So here are some key features of hyperbolic geometry. So first is divergent parallel lines. Unlike Euclidean geometry, where parallel lines never meet, in hyperbolic geometry, two parallel lines diverge farther apart as they extend. This creates a sense of openness and expansion in the hyperbolic spaces. So second is triangle angle sums. In Euclidean geometry, the sum of angles in a triangle is always 180 degrees. However, in hyperbolic geometry, the sum of angles in a triangle is always less than 180 degrees. This deficit is called the angle defect and increases as the triangle becomes larger. So third is negative curvature. While Euclidean geometry has a flat or zero curvature, in hyperbolic geometry has a negative curvature. This means that space curves away from itself, creating a saddle-like shape. 4 is infinitely many centers of a circle. In Euclidean geometry, a circle has a unique center point. However, in hyperbolic geometry, a circle can have infinitely many centers, all of which lie on a line called the horocycle. Fifth is non-compactness. Unlike Euclidean space, which is boundless, hyperbolic space is non-compact. This means that any point in hyperbolic space can be reached by traveling a finite distance, but the space itself extends infinitely in all directions.
Welcome to the world of hyperbolic geometry, a mathematical realm that applies the familiar rules of Euclidean geometry we learn in school. In hyperbolic geometry, lines take unexpected paths, and triangles have angles that add up to less than 180 degrees. In hyperbolic geometry, the concept of parallel lines takes on new meaning. Given a line and a point not on it, there can be a multiple line parallel to the original line through that point. It challenges our intuition but opens up a fascinating space of possibilities. Imagine a triangle in hyperbolic geometry. Its angles don't conform to the familiar Euclidean sum of 180 degrees. Instead, they add up to less than 180 degrees, and this non-conformity with our everyday experiences is what makes hyperbolic geometry so intriguing. One of the defining features of hyperbolic geometry is its negative curvature. Unlike the flatness of Euclidean geometry, hyperbolic space curves in a unique way. This constant negative curvature creates a distinct geometric environment. To help us visualize hyperbolic space, mathematicians use the Poincare disk model. In this model, the entire hyperbolic plane is mapped within a unit disk, preserving angles while distorting distances. Hyperbolic space allows to mesmerizing tilings with regular polygons, a feature not possible in Euclidean geometry. These intricate patterns reveal the unique nature of hyperbolic geometry. As we delve into the depth of hyperbolic geometry, we discover a world where parallel lines are not bounded by the rules that we thought were universal, where triangles defy our expectation, and where space itself takes on a distinctive curvature. This is a glimpse into the fascinating realm of hyperbolic frontiers.
Application of hyperbolic geometry. Hyperbolic geometry has a various applications in mathematics, physics, and computer science. Some notable example includes Riemannian geometry and general relativity. Hyperbolic geometry plays a crucial role in understanding the curvature of spacetime and the gravity field. Coding theory. Error-correcting codes and data comprehension algorithms can be designed using the principles of hyperbolic geometry. Fractal geometry. Hyperbolic geometry provides a framework for understanding and classifying various types of fractals. Computer graphics and animation. Hyperbolic models are used to create realistic representation of curved surfaces and complex shapes. Non-Euclidean robotics. Hyperbolic geometry can be applied to develop robotic systems that navigate and operate in non-Euclidean environments, such as underwater or inside complex structures. Hyperbolic geometry is a fascinating branch of mathematics that challenges our conventional understanding of space and geometry. It opens the doors to new perspectives and applications, further enriching our understanding of the world around us.